Hi everyone, this is our presentation for the Auto Insurance Loss Ratio Prediction Project for DSB 6100 with Cal Amakan, Vijay Soon, Pooja Hosheti, and Tian Wong. We are Team 3 and we hope you enjoyed today's presentation. This is a brief outline of what we will be discussing today. 1. We will briefly introduce the main subject of our project, what our essential problem was, and our goals. We will then discuss our personalized strategy for approaching the project that included exploratory data analysis with descriptive statistics. We will then break down our solution for the project. This included extensive data wrangling, feature engineering and selection, encoding, train and test data preparation, and the modeling phase. Lastly, we will discuss the challenges we faced while working on this project, and most importantly, what we have learned. So let's get started with a brief introduction. When starting this project, we realized right away that we must understand the background of the project before pursuing further. This includes understanding the importance of auto insurance in regard to real-world applications. With auto insurance being an important contract between individuals and an insurance company, it is certain that individuals are frequently relying on the best vehicle protection against liability, physical damage, or bodily injury from vehicle collisions. With this background information, we were able to determine our essential problem. Organizations are suffering a loss from insurance policies being overpriced by up to 50%. With these surprising statistics, we realized our goal was to build an optimal, robust model that could accurately determine and calculate present liability with future claims and the expected loss for portfolios. We also knew it was important to understand exactly why we wanted to predict this, and this is to help businesses make high-level decisions on rates for each policy portfolio. To attain this required goal, we had to compute the natural logarithm of the expected loss ratio. Now that we had a thorough understanding of the background of our problem and the detailed goal of what we were trying to reach, we had to write out a strategy to reach this required goal. Our strategy consisted of deeply analyzing the data set for any discrepancies. This includes noise, unusual trends, inconsistency, and human errors. We then dropped irrelevant attributes through initial analysis and human judgment. Next, we performed extensive data wrangling and imputation. Following, we one-hot encoded categorical data to have consistency in the dataset. Then we applied various machine learning model techniques. Moreover, we evaluated each modeling technique to finalize the best fit. And lastly, we applied the chosen model on the test data to upload onto Kaggle for evaluation. Exploratory data analysis is an essential part of the data mining process. We as a team took this as an opportunity to explore and truly understand our data, as this stage would greatly affect our final predictions. With that being said, we used Google Open Refine for initial data analysis. We searched for interesting patterns in the data through descriptive statistics. Since we proposed using linear regression, we had to be cautious of outliers from the beginning. Policies with loss ratio more than 1,000 were identified as outliers. In addition, there were 60 out of approximately 20,000 non-zero records. This was equivalent to 0.03% of valid records and almost 0% of the entire dataset. We also determined that columns vehicle coverage limit and vehicle cost amount had more than 90% of the data missing, so we determined it may be an insignificant feature to include. Also, column vehicle days per week had values of more than 7, which did not seem logical considering there's only 7 days a week, so values could not exceed 7. With this in mind, we were already moving towards a cleaner data set. Now we could continue the big data process with an efficient solution summary. Our solution was done in 3 phases: data wrangling, train and test data preparation, and developing and testing predictive models. The next slide highlights data wrangling, how we were able to handle bad data. We organized it by explaining the data issue and our reasoning behind why we took a particular action. For instance, if more than 90% of the data was missing in the column, we dropped it. Similarly, 7,000 distinct records were grouped into 53 distinct vehicle brands instead, using a clustering technique. For instance, for vehicles with description Toy or Toya, were replaced with Toyota. Similarly, zip code had 1640 distinct values. we considered first digit the state code and shortlisted zip to 9 distinct records. Once we were done with data wrangling, we focused on feature selection, where we had to choose the most relevant feature that would best help us make better predictions and have better results. We tried various techniques, which include the chi-square technique with select k-best. We also applied categorical columns feature selection by using ordinal and label encoding. We also applied feature selection with the random forest regressor and a correlation matrix. As exemplified in the image to the right, the features with relatively less scores were removed, and we rechecked the model's performance in comparison to when the features were still present to see if it made a noticeable difference. As mentioned on the previous slide, we implemented a heat map to visually see how the features interacted with one another. We took the issue of multicollinearity very seriously, as we wanted to avoid a column being highly correlated with one or more other columns in the dataset. With that being said, we dropped the following columns displayed on the left from our model. This slide primarily explains the composition of train and test dataset. Training dataset was prepared with 339K records, with 15K with non-zero loss ratio. Similarly, testing dataset was prepared with 18K records, with 3K non-zero loss ratio. We further divided test and train datasets into portfolios, where each portfolio comprises of approximately 5K records. This slide also highlights the change in the mean and median value before and after removal of outliers. With these important findings, we had to understand what exactly we were trying to build. We wanted our model to firstly summarize each portfolio to one record and compile a new file with a summarized entry for each portfolio. We would then use that new file that we compiled to train our model for predicting loss ratio. Once the model is finalized, the test portfolios will be tested by predicting the loss amount and then calculating the loss ratio. This image highlights our strategy, the test results from multiple testing portfolios. With this strategy, we implemented many models to compare metrics, first being the light gradient boosting technique. Similarly, we also implemented ridge regression with cross-validation and the L2 regularization penalty. Lastly, we implemented a random forest regressor. We tried a simple random forest regressor, but aimed to improve the metrics by performing hyperparameter tuning with grid search CV, which granted us the best estimators for that particular model. These are some results for each of the models that we implemented. When comparing the relative performance of the three models, we noticed that random forest with grid search CV was the most suitable, as the difference of error between the train and test dataset was relative. With all the information in mind, the real test was predicting values for our actual dataset through the following steps. 1. Wrangling the actual test data as per the defined data wrangling protocols. 2. Calling the prediction object to predict the loss ratio for the respective portfolio. 3. Loading the predictions in an output result CSV file with two columns, the portfolio name in the ID column and the log loss ratio column. As exemplified in the image to the right, that is the CSV file we submitted for the Kaggle competition. Throughout the process of this project, we did face some challenges. Extensive research had to be done on each team member's part to truly understand the components of auto insurance and gain a solid foundation of the topic to make the best data-driven decisions for the project. In addition, the pre-processing stage was tricky, but we knew that up to 80% of a data scientist's time is spent in the pre-processing stage. Despite the challenges, we learned a tremendous amount of concepts throughout this project. Each team member had great ideas individually, and we were able to express our optimal model ideas through frequent team meetings, which in turn enhanced our knowledge of the subject and our collaboration skills. Overall, this was a very insightful and exciting project and validated how big data can be applied to endless numbers of real-world applications. Thank you to the following references, resources, our TA, and our professor for being a helpful guide for our project. And thank you so much for listening to our presentation. We really hope you enjoyed it.